do the next lesson, we're going to talk a little bit about the end of the year stuff, and then we're going to be done for today. Yes, sir?
Do we know when our test is yet?
For this chapter, next week.
Or what?
Next week.
Oh, like the end of the week or the beginning of the week?
We'll have a review day and then the test.
Okay.
So Wednesday.
That's what it's looking like.
Wednesday? Okay. Why?
That's my tentative plan without going and looking at anything else going on that day.
So next week.
Next week needs to get done next week, for sure.
I just saying anything wrong. I have to ask it every test.
It's a reasonable question, man.
Apparently I'm not allowed to ask.
No, yeah, no, you will have to talk to him after that one video.
All right. Landon.
Can you do number 12?
Number 12. Sure. So these are expanding problems. For number 12, remember the order for expansion is quotient, product, power. Now obviously there's no quotient property, there's no division going on. I do see two multiplication symbols, so that's two product properties. So I can basically just put a plus sign, kind of where each one of the pluses, or where the multiplication would go. And then I do my power properties. There's one power property on the z to the third. That's it. Bada boom, bada bang. Dunzo, funzo. Who else, or what else, or anything else?
Um,
25? Sure. For 25, what I would probably do is get rid of, kind of clear the parentheses out of here to start, and then we'll do some rearranging. So I'm going to distribute the 2 through, and also distribute this negative through. That. So when doing a condensing problem, I'm going to first do my power properties. So here, because I have the 2x on the inside, that power of 2 needs to apply to the whole 2x. And then also the 5 squared, I'm just going to write as 25 at the end. Next thing I would want to do is look for product properties. There's actually 2 product properties hiding here. So remember, with the quotient property, there's really ever only one quotient property. So I see all these subtraction symbols, but I can just kind of like think about factoring a negative out of there. Like that. So there's really 2 product properties going on here with the 2 plus signs. So 3 times 25 is 75. I'm going to multiply those things together here. So just write it that way. Is that okay? And then finally, I'll do my quotient property. That's my final. Yeah, I mean, the trick was, in the beginning, deciding to like clear all the parentheses out of there. If you tried to do it with the parentheses there, it gets a little bit confusing what to do.
So the
I think that makes the problem easier, because then you can just do the regular order that you're accustomed to, rather than going in the order the parentheses are implying. In addition, because you had like kind of two quotient properties going on there, if you don't clear the parentheses out, then like what the heck do I do with this fraction, f a fraction thing, is also kind of confusing, but you don't have to deal with that if you clear the parentheses. So that's usually my advice, is to clear the parentheses using kind of our properties, and then we can go back to the standard order. And that goes whether you're doing expanding or condensing. You know, there's a couple of condensing problems, or expanding problems like this one. You know, like I would start by, you know, like turning that third root into the exponent. And then I would do like the exponent of a product property. And then I would start my expanding. And now you don't have to go outside of the regular order, because really you have this extra set of parentheses inside the logarithm that would tell you to do a different order. But like, I'm all of the mind, like, clear all the parentheses out of there, and then you can do just the regular expanding and condensing order. Typically things are easier if you do it that way. I mean, it's not always the case, but I think the things that we'll see in this class, it would certainly be the case. Or at least more obvious what to do. Maybe easier is the wrong word, more obvious. And then this one, obviously, like, you do some stuff, but it ends up like 1/3 log x plus 1/3 log y plus 1/3 log z. And I skipped some steps there. I just wanted to write down the answer to make it feel like I didn't just finish the problem there. I just got it to the starting point where I would start doing the expanding stuff. Yeah, go ahead, dude. Other questions on this assignment? Artichokes. So today we're going to talk about solving. And there's two types of solving problems we're going to talk about. So we're going to talk about exponential equations and logarithmic equations. So let's say that we have the equation 4 to the x plus 2 equals 8 to the x plus 3. In a problem like this where we have two exponentials equal to each other, the preference would be to try to rewrite these so that they have the same exponent base. Sometimes that's easy to do, and sometimes that's really difficult to do. If it's difficult, we'll do something different. But in this case, it's rather easy to do that. If you observe 4 and 8, those numbers have something in common, specifically that they're both powers of 2. So that's what I would do first. I can rewrite 4 as 2 squared, and 8 as 2 to the third. And then the exponents from before just kind of come down with them. From last chapter, you remember that if you have an exponent of an exponent, the exponents multiply. And then I can just kind of distribute those through. Everybody still doing okay? Now here, if I have 2 to some power is equal to 2 to some other power, what I can say is that those 2 powers must be equal, right? If the bases are the same and the 2 things are equal, the only way that can happen is if the 2 exponents are equal, right? So I can just kind of forget about the 2's. And then just solve this like a linear equation. So I'd subtract 2x from both sides to get x, and add 9 to both sides to get 13. So far, so good? So what if we have the same problem, except we have 2 numbers that it's not trivially easy to rewrite them so that they have the same exponent base. Right? 4 and 2 are not both powers of the same number easily, right? 4 is 2 times 2, but 6 is 2 times 3. It's got that extra 3 in there. Everybody see the difference between this one and the previous one? So I'm going to do something different here. Keep in mind that the method I'm going to use here, I could use in the first case also, but it's a little bit more mathematical firepower, so to speak. So I showed you this other way first. So in this case, where I can't easily rewrite these to have the same exponent base, I'm going to use a logarithm. So the question becomes, what logarithm? Do I want to use log base 2 or log base 5 or log base 1.7? Which logarithm should I use? The answer is, it doesn't matter, but you can make your life a little bit easier by picking one of 2 specific logarithms in this case. The easiest way to do this would be to pick a logarithm whose base matches one of the exponentials in your problem. So for this problem, I would either pick log base 4 or log base 6 would be the easiest thing to choose, although any logarithm will be fine. But let's not make the problem harder than it needs to be. Let's say, for the sake of argument, let's do log base 4, right? Doesn't matter whether I did log base 4 or log base 6, but let's just, for the sake of argument, do 4. So I'm going to do that to both sides of my equation. Everybody so far so good with what I've written down here. Now I know that log base 4 cancels exponent base 4. So on the right-hand side, I'm left with just the x plus 2 from the exponent. On the right-hand side, I'm going to use the power property. That allows me to move the x minus 3 to the coefficient, just like we would have in last night's homework. Everybody's okay with that? Now keep in mind, log base 4 of 6, that's just a decimal, right? That's just some number, like the square root of 2 is just a number. And in fact, if you wanted to, if it makes your life easier, you could fire up your calculator and replace log base 4 of 6 with the decimal. In this case, log base 4 of 6 is, I don't know, 1.2 something probably. Now, 1.292. And then you can just distribute that in. And then what is 3 times that? I'm not doing that in my head. 380 or 3877. And I'm just rounding these to 3 decimal places. That's would be my direction for you guys on an assignment or a test or something on these solving type problems. And now this is a pretty easy problem, right? I'm going to subtract x from both sides. That'll give me 0.292. And then add 3877 to both sides. That gives me 5.877. And then we'll just divide both sides by 292. And I get about 20.128. Is everybody okay with that? So the trick there was to use a logarithm, right? And ideally, you pick a logarithm that's going to cancel one of the 2 exponent bases. That makes life a little bit easier because there's just less decimals to have to worry about. But you could have picked like log base 10, and then you would have had 2 decimals to distribute through on each side, but you'd end up with the same answer in the end. But it just makes it a little bit simpler to do it that way. Lynn?
So you could have done log 6, like it doesn't matter which one you choose.
Correct. Yeah. And in fact, you didn't even have to do log base 4 or log base 6. Like any log, you could still get the same answer. It just may be a little bit more work. But the log base 6 wouldn't have been any harder, right? It just would have been the right side. You have the x minus 3 on the other side, you'll have a decimal.
I think I got it, but for like the second part, how did you get 0.292 again?
I typed that into my calculator.
No, like, you know how?
Oh, I subtracted 1x from both sides,
Oh, okay.
right? So it's x is really 1x. So
Yeah.
1 minus 1.292 just becomes 0.292. Yeah, it's okay. It's easy to kind of forget about those coefficients of 1 sometimes. Everybody okay with that particular type of problem? Okay. The third type of problem that we'll see for exponentials is something like this one. So here I have only one exponential in the problem, right? Different than the other ones where we had 2 exponentials. And we have some other stuff that's not exponential at all, right? We have some coefficients and constants kind of floating around here also. In a case like this, my goal is going to be first to get the exponential part by itself. So I would subtract 6 from both sides to begin. And then divide both sides by -3 afterwards. And now the exponential part is by itself, right? Now, just like the previous example, or the previous examples, I could at this point try to rewrite them to have the same exponent base. But in this case where I have e, remember that's a number, like that's that 2718, yada, yada, yada number from a couple lessons ago. And 3, there's not an easy way to do that, right? So instead, I'm going to do the same thing I did before and use a logarithm. Now here, there should be an obvious choice about which logarithm to use to make this as easy as we possibly can. Which logarithm would I want to use? Log base e, which the abbreviation for it was ln. Remember, that was one of the special logarithms that has a special symbol. So that's what I would do here, is take the natural log of both sides. ln is short for like logarithm natural, because the mathematician that generated it was French. In fact, most of the academic stuff being done at that time was probably in French. To depending on when this was developed, it very well could have been even before Germany was a formal country. So Germany as a nation didn't come in until like the mid-1800s, which is odd to think about. There was other, like Prussia was there, there's some other republics there before Germany, but Germany as a nation wasn't established until the middle 1800s, which is weird to think that it's that young of a country, even though like it's clearly not a young country, right? But anyways, so France and Germany were doing a lot of the mathematics on the continent, and even like a lot of the English intellectuals spoke French and did a lot of the writing in French. Anyways, so yeah, those cancel. So I have 4 minus 3x, and the natural log of 3 again, just a decimal. So we could go to our calculator and type that in. So what's that? 1099. And then I can subtract 4 from both sides. And use the calculator to do that because, yuck. Too many decimal points for me to carry at this hour. Negative 2.901. And then we'll divide by negative 3. And I have 0.967. Is everybody okay on that? So that's the second, or the third type of exponential kind of problem. That's all the types that we're going to worry about in this course. I mean, there's other things, but they're beyond the scope of what we're going to do here. So the 3 different methods depend on whether you have 1 exponential or 2. If you have 2 exponentials, you either try to write them with the same base, or even in that case, you could use a logarithm. Either works. The first example I showed you is where we rewrite them with the same base, but you could have used like log base 4 or log base 8, or even a different log. All still could get to the correct answer. Any of those options is fine. I have no preference there on what you do. In a case where it's not easy to rewrite them with the same base, you're really kind of stuck with using a logarithm. The easiest way to use that logarithm is to use the log base to match one of the exponential bases. But you don't have to. You could pick some other log and it'll still work out. So maybe a little bit more decimals rattling around in there, but it's not the end of the world. In the third case, where you have just 1 exponential, you kind of treat it the same way a normal solving problem is, where we isolate the exponential part, and then use the logarithm whose base matches that exponential, and then finish up solving from there. Is that okay with you guys? That last one very much should remind you of like solving a square root equation from the last chapter, right? Instead of canceling the square root part, we're canceling the exponential part, but it's kind of the same order of operations, even though the steps, or the same steps, even though the operation involved is different. All right. Let's look at some logarithm examples. Here's some logarithmic equations. So one situation here is where we have just one kind of logarithm, or one logarithm in the problem. In a case like this, what I'm going to do is I'm just going to treat it very much the same way we did the previous exponential problem. I'm going to get the logarithmic part by itself, and then we'll cancel the logarithm using an exponent base. and then finish solving. So the first thing I would do is subtract 8 from both sides. And then we'll divide by the negative 3. And then to cancel the logarithm, we need to use an exponent base. So what number, in this case, should I use as my exponent base?
2.
2. Why 2?
Because that turns into 1.
Because it matches the base on the logarithm. Exactly right. Okay? So we do have to be careful here. You need to make sure the exponent base you're using matches the base on your logarithm. And I'm going to write my exponent base pretty big, so nobody mistakes it as me multiplying both sides by 2. Everybody's okay with that? My suggestion to you would be to do the same. It's very easy to get confused and multiply instead of using an exponent base. So those things cancel. We're left with x plus 4. And then 2 to the third is 8. And then we just need to subtract 4 from both sides. But we're not done. The logarithmic equations can have extraneous solutions, so we need to make sure we're checking our equations. The check, however, is quite easy. All you need to do is go back to the original equation. Maybe I should pick the same colors. Plug it inside the logarithm or logarithms if there's more than one. And you just have to make sure the stuff inside the logarithm is positive. That's greater than 0. So 4, if I plug that in, 4 plus 4 is a positive number. So that answer is fine. Everybody's okay with that? The place where we get in trouble is if we have a 0 or a negative inside of our logarithm. But as long as that whatever we plug in is positive, and we did all of our steps right before that, everything's landed.
So say you did get like a negative number, what would you do? Like, does that mean you did the problem wrong?
No, it just means that that answer is extraneous. In this case, if that's our only answer, we cross it out and say no solution. Let's do another example. Okay? So this problem is different than the previous one, right? Because in this problem we have 2 logarithms and some stuff that's not a logarithm, right? Because we have that 1 at the end. Everybody agree? My goal here is to turn this into a problem like we did before by taking those 2 logarithms, condensing them into a single logarithm, and then I'll proceed like I had in the previous problem. So my plan here is to take this and to condense it. Just like we did in last night's homework. So there are no coefficients, so there's no power property to do. The next thing I'd look for is the product property. I do see an addition symbol. So I can apply the product property. And obviously there's nothing left, there's no subtraction, there's no quotient property. So this is all I can do for my condensing. At some point we're going to have to multiply that stuff out. I guess I might as well do it right now. So I'll just distribute the x through. And now I'm going to cancel out my logarithm. So to cancel this logarithm, I need to use an exponent base. What number should I use for my exponent base? not 1. So you said 1 because you don't see a number written as the base for the logarithm. 10. Remember that there are 2 special symbols. There's ln, which is log base e. And then there's log with no base written. That's log base 10. So log base 10 is the common log. ln is the natural log. So this one we understand the base to be 10, even though it's not written there. Lily? Okay. So that is a special symbol. When we write log, we understand that the base is 10, even though we didn't write anything there. Just in the same way we understand the index on a square root is 2, even though we don't write the index inside the square root symbol. It's one that we use a lot, so we're just going to shorten it up. So the log base 10 and exponent base 10 cancel. And look at what we're left with. What kind of an equation is x squared minus 3x equal to 10? Starts with a Q. Quadratic. To solve a quadratic equation, it must equal 0. So I'm going to start just by subtracting the 10 over. And then our 2 primary methods for solving a quadratic would be to factor or use the quadratic formula. In a case like this where the leading coefficient is 1, typically I'm going to start by trying to factor it, because if it is factorable, it should be pretty easy to do and a little bit faster than the quadratic formula. If I can't figure out how to factor it, it could just be not factorable, in which case I'd have to use the quadratic formula. Or maybe I'm just having a bad day and I can't figure out how to factor it. I can still use the quadratic formula in either case. But here, this is definitely factorable. The 2 numbers that multiply to give me negative 10 and add to give me negative 3 are, well, that would add to give you positive 3. You want negative 5 and positive 2. You were so close. So I can then, once this is factored, set each factor equal to 0 and solve. And I get 5 and negative 2. But I'm not done. What do I still need to do? I need to check. So I go back all the way to the beginning. Let's check the 5 first. That was the first answer we found. If I plug 5 in for x, that's positive. If I plug 5 into x minus 3, 5 minus 3 is 2. That's still positive. 5 is good. Let's check our next answer, which is negative 2. If I plug negative 2 in for x, I get negative 2. So I don't care what happens after that. I've seen enough. I know this one is good, and this one is not. Doesn't mean we did anything wrong. If you actually want to check to see if you've done anything wrong, you have to plug it into both sides. You know, plug it in everywhere and make sure that simplify to make sure the 2 sides are equal. You don't have to do that much to check for extraneous. We just need to make sure that the stuff inside the logarithm isn't a negative number. Or, sorry, has to be a positive number. 0 is bad also. All right, we have one more situation for logs, but it's actually the easiest of the 3 situations. Yes, sir. Of course. What do we got here? So let's look at this one. We got log base 1/2 of 2x plus 7 equals log base 1/2 of x plus 2. So this problem we have two logarithms, and we have nothing that's not a logarithm, right? This is the easiest situation if they're set equal to each other like this. Because really, this is the same idea that we had right here. Right? If you had two exponentials with the same base that are equal, the exponents must be equal. If we have two logs with the same base that are equal, the insides have to equal. Everybody agree with that? So we can just forget about the logarithms here. And then some. So this is pretty easy. I subtract x from both sides, I get x, and I subtract 7 from both sides, I get -5, so x equals -5. If I go back and check that, though, 2 times -5 is -10, plus 7 is -3. Ruh-roh! So I threw out my only answer, so I write it. What I write is no solution. Yes, sir.
Why are we getting rid of the logs again?
So the analogy that I drew was back to this problem where when I had the two exponent, like the exponent bases were the same and they were equal, it means the exponents have to be equal. So if I have two logarithms with the same base that are equal, the insides also have to be equal, right? That's what we did there. So we just dropped the logs because they had the same base. Yeah. And they were equal. Now if there's like a +1 at the other side, you can't do what we just did. Or if one was log base 2 and the other was log base 3, you can't do what we just did. But those situations are beyond the scope of what we do in this class.
So if they're both the same base, which is like the same number, that's which comes out.
Right. Yes. Yes. Okay. Any questions from you guys? This is basically the gist of it. There's much harder problems than these, but I think they're beyond the scope of what I need to see from you guys. Or more variety of problems even than this, but again, I think these are the most common kinds of problems that I'd expect to maybe you see on like an ACT or something like that. So I wanted to make sure we kind of do enough to where, you know, when you take a standardized test or whatever, you're like, oh, I've seen how to do this before. And maybe you don't remember how to do it then, but at least you recognize it's like, okay, this is something we did in class, which is the minimum of what I'm shooting for, right? At least you're like, oh, well, we talked about this.